Okay, an introduction to molecular orbital theory. We have been studying valence shell electron pair repulsion theory as our main theory for modeling compounds and what we think is going on with compounds. I love valence shell electron pair repulsion theory. It is excellent at explaining geometry of molecules. You know, we have some very clear evidence in terms of bond energies and structure that would support valence shell electron pair repulsion theory. But as in any modeling of something that is unseen or unknown, sometimes we have to modify that. And molecular orbital theory is a modified modeling theory, and it really is able to explain some things that valence shell electron pair repulsion theory cannot. So why molecular orbital theory? Um, as I mentioned, this valence shell electron pair repulsion theory explains geometry very well. And if you remember your hybridized orbitals that give us our bond angles, um, you know, that works. We know that to be the case. However, it does not explain resonance. With valence shell electron pair repulsion theory, a double bond should have a different energy than a single bond does, or a different bond energy. But in molecular orbital theory, all of the bonding orbitals are the same, so there is no double versus single bond. And because all of the bonding orbitals are the same, they would all have the same energy and the same length. So there is no difference in a single bond or a double bond or a triple bond in molecular orbital theory. And molecular orbital theory explains well the existence, now it is a rare existence, but the existence of some ions in the diatomic state, like diatomic lithium. You know, that's probably not something you've heard of before, and it does exist. It is rare, but molecular orbital theory can explain why that does happen. So a little bit of background on molecular orbital theory. Please remember that electrons move in waves. So we have to consider wave interference, and there's two types of wave interference. We have constructive interference, meaning that waves are in phase, meaning their crests are occurring at the same time. And when the waves are in phase with each other, they will add together. It's like if you have, you know, an amplifier which catches a wave and then matches its phase, it will make that sound much larger than it was. If you think about an amplifier on a guitar string or electric guitar string, you pluck the string vibrates. When the amplifier matches the same wave frequency as the wave being plucked by the guitar, then those waves become additive, and you can hear the noise that guitar string is making. Or they can be disruptive. So when the waves are out of phase, they will cancel each other out. I've got a picture here to show you, if you want to wait a minute for that. So we have the first two waves that are on this slide are waves that are in phase, and they will add together and equal a much larger amplitude wave. So what they're showing are these two waves that are in phase, that you know, their crests are in phase like that. Oops, I don't know if I can do that. Can I do that? Nope, I cannot, sorry. So the waves are in phase, they will add together and amplify. Destructive interference, the waves are out of phase. A crest meets a trough instead of a trough meeting a trough, and a crest meeting a crest. And when they have destructive interference, they completely cancel out the wave. So no wave is there. And keep that in mind when we're dealing with because we have constructive and destructive interference, we also have, for molecular orbital theory, we have constructive and destructive interference with electrons, which produce bonding versus non-bonding orbitals. Okay, so interference and the molecular orbital theory. Orbitals combine in a simple linear fashion. You'll see that LCAO means linear combination of atomic orbitals. So the orbitals of atoms combining. Constructive interference and bonding orbitals. Bonding orbitals have a lower energy than the atomic orbitals from which they are formed. So you have atomic orbitals that are not bonded. When they produce a bonding orbital using constructive interference of the electrons that are moving in waves to bond with something else, so these electrons are in phase, that's going to produce a bonding orbital, and that bonding orbital has lower energy. Destructive interference. So you have electron waves that are not in phase, and or the orientation of the orbitals is not correct. So you have this p orbital, but it's not overlapping with an s orbital to make a bond. Then that is destructive interference, and those produce anti-bonding orbitals. And those anti-bonding orbitals have higher energy. So you have bonding orbitals and anti-bonding orbitals. Bonding orbitals have low energy. This is what the universe likes. Constructive interference or anti-bonding orbitals are of higher energy. So you might have a 1s orbital that is a 1s bonding orbital, and then you might have a 1s anti-bonding orbital, where you have electrons in phase and out of phase. Okay, so what should you be able to do with this molecular orbital theory in terms of what does the College Board expect from you? You should be able to draw molecular orbital diagrams. You, however, do not have to produce the molecular orbital structure, the order of the molecular orbitals. That will be provided for you. You should be able to calculate the bond order and predict the particular stability of a compound. To calculate bond order, you should be able to predict paramagnetic and diamagnetic properties. We're talking about paired versus unpaired electrons. And to calculate the bond order, back to that, I'm sorry, I have that out of order. We will take 1/2 of the number of electrons in a bonding orbitals minus the number of electrons in anti-bonding orbitals, and we'll take 1/2 of that number. So electrons in bonding orbitals minus the electrons in anti-bonding orbitals divided by 2. We'll calculate bond order in molecular orbital theory. Bond orders that are greater than 0, we would predict that that's a stable arrangement and that compound probably exists. Bond orders that are less than 0 or equal to 0, we would predict that compound does not exist. It's not stable. So you need to predict paramagnetic or diamagnetic properties. Of course, that's all about unpaired electrons. We've learned that before. So paramagnetism, unpaired electrons, diamagnetism, repelled by a magnetic field, and that has no unpaired electrons. So diamagnetism is a new word for you, but paramagnetism is not. Okay, how do orbitals combine? Oh, oops, sorry, didn't even see that there. Oh, you only have to do this. That is, draw molecular orbital diagrams, calculate bond orders, and predict paramagnetic and diamagnetic properties. We only have to do that for periods 1 and 2 homonuclear diatomic species. Think about the words. Homonuclear, meaning the same nucleus of diatomic species. So 2 atoms of the same kind bonded together in periods 1 or 2. That's all you have to do this for. And then period 2 homonuclear and heteronuclear diatomic species. So diatomic elements that are of the same atom in period 2, but also you'd have to do diatomic elements of different atoms that occur in period 2. So like maybe carbon monoxide. Carbon and oxygen are both period 2 elements. That is a diatomic molecule because it's just 2 atoms, and it is heteronuclear. Okay, how do orbitals combine? So I'm going to pause this here and start a new video because I need to get to my whiteboard. So stop this here. If you need to go back and take some notes, please do that and get what you need from it. If you need to look through the slides again and get definitions, do that. And then we're going to move on to actually doing something with molecular orbital theory.